One of the great linear valleys of the world occurs in the North American Cordillera, where it extends over 3,000 kilometers from Alaska to Montana. Many workers believe that the northern sector contains the Tintina Fault with over 400 kilometers of right lateral displacement, whereas the central and southern sector, collectively called the Rocky Mountain Trench, contains dominantly normal faults. Thus, the origin and significance of this valley are enigmatic. And here I hope to summarize part of my recent paper, where I suggested that the trench is the locus of a strike-slip fault with about 1,300 kilometers of dextral displacement. Over the 50 years since Beck and Nosen first discovered aberrantly shallow, far-sided paleopoles for Cretaceous rocks within the Cordillera, numerous other paleomagnetic studies were completed with more or less congruent results. But geologists could not find the faults on which to move Cordilleran fragments northward, so commonly blamed the paleomagnetic methodology. As a way around this, some researchers such as Tikoff, suggested that the missing faults were terrain boundaries, and that most, if not all, of the northward migration occurred offshore. But the problem with utilizing terrain boundaries within the Cordilleran tectonic collage is that the main period of northerly migration largely postdates terrain amalgamation, with rocks as young as the 70 million year Shoshonetic Carmax group of the Yukon Territory yielding 1950 plus or minus 600 kilometers of apparently northerly migration. As you can see here, this is mostly within error of the other Upper Cretaceous Paleocene Cordilleran bedded units with large displacements. I only use bedded rocks for paleomagnetic analysis, as it is impossible to confidently ascertain paleohorizontal and plutonic rocks, especially because they are commonly folded or tilted. For bedded rocks in the range of 90 to 70 million years, deviations from the mean are approximately an order of magnitude lower than the overall mean translation of 2,100 plus or minus 700 kilometers, documented by Randy Enkin way back in 2006. Thus, the majority of the northward migration occurred after about 70 million years, when all terrains except Silesia had already docked. As pointed out years ago by both Randy Enkin and Stephen Johnston, the northward migration must involve rocks as far east as the easternmost outcrops of the Carmax group, which collectively span the intermontane belt from the Tintina Fault westward to the Denali Fault as shown here. Note the few occurrences within a few kilometers, but I think about 7 kilometers, of the Tintina Fault. Northward migration ended by about 52 plus or minus 2 million years ago, as documented by several studies, which found coincident paleolatitude from rocks of the insular intermontane sector of the Cordilleran hinterland and those of Cretonic North America, as you can see here. Thus, the bulk of the dextral or northward meridional migration within the Cordillera took place between 70 and 52 million years, which, if correct, sets up a set of conflicting problems. First, the easternmost paleomagnetic samples, those collected from volcanic and epiclastic strata of the Carmax group, occurred just a few kilometers west of the Tintina Fault, as we've seen, which lies along the northern extension of the Rocky Mountain Trench, and is generally considered to have but 400 to 430 kilometers of Eocene dextral displacement. This interpretation conflicts with the 750 kilometers to more than 900 kilometers of displacement of Paleozoic sedimentary facies suggested by Hugh Gabriels of the GSC, and the 2,000 plus or minus 700 kilometers of dextral displacement indicated by paleomagnetic studies of the Carmax group. Although the truncations of many unit structures and contacts on either side of the fault were utilized in attempts to constrain strike-slip displacement, none provide convincing matches. Second, several erosional remnants of the Carmax group, close to or even upon lower Cambrian platformal rocks of the Cassiar Platform, which is truncated to the east by the Tintina Fault where it is juxtaposed outboard or west of the outer clastic belt within the Selwyn Basin, located on the other side of the fault. The Cassiar Platform comprises a west-facing complex of algal archaeocyathon mounds and intervening oolitic grainstone shoals, minor shale, and calcilite, which Pope and Sears argued to have been deposited more than 1,000 kilometers farther south in Idaho, where there is a conspicuous gap in the early Cambrian carbonate platform of western North America. The third thing to consider is that, as pointed out by Enken, the Tintina Fault cannot have significant Eocene slip, as the paleolatitudes from Eocene units in the hinterland west of the fault have coincident or Tectonic paleolatitudes. Fourth, the Omineca metamorphic plutonic belt, which largely lies west of both the Tintina Fault and the Rocky Mountain Trench, is the eastern of two metamorphic plutonic crystalline belts in the Canadian Cordillera, as shown here. The rocks in the Omineca belt were deformed, metamorphosed, and impregnated by plutons between 124 and 105 million years, and it seems out of place in its current location, as there is no temporally comparable deformation in the foreland fold and thrust belt to the east. This graphical illustration of mismatched deformational ages for the Great Basin and Canadian sectors of the Cordilleran origin shows the relations. In the Great Basin area, rocks of the North American Platform Terrace were deformed and thrust eastward during the 125 to 105 million year severe event. Yet rocks to the west in the Great Basin show no evidence of this deformation. The opposite holds true for the Canadian sector, where rocks of the North American Platform Terrace have a well-developed Santonian to Eocene Laramide fold thrust belt, but rocks to the west have severe age deformation. These and other data suggest that the arc and hinterland of the severe event are now resident in the Omineca belt of the Canadian Cordillera. This mismatch is supported by the presence of the Bourgeot thrust, which has Santonian, Campanian marine shales in its footwall syncline. However, just to the west, where Paleozoic sedimentary rocks sit atop metasedimentary rocks of the Mesoproterozoic Purcell supergroup, thrusts were shown to predate 109 million years, because they are cut by syn to post-kinematic plutons. These observations led me to argue that the Omineca belt was the metamorphic plutonic hinterland of the 124 million year severe orogeny of Utah and Wyoming. Fifth, field mapping and uranium-lead dating along the Salmon River suture of Idaho indicate that rocks of the Blue Mountain superterrane and those of the Bell-Purcell-Windermere package were juxtaposed prior to 110 plus or minus 5 million years, as indicated by the age of the intrusive Little Goose complex which cuts the contact. Subsequent deformation, interpreted as transpesonal deformation within the Idaho shear zone, overprints the suture and is older than 90 million years on the basis of uranium-lead ages of non-deformed granitic pegmatites that cut the fabric. Robust paleomagnetic data collected by Bernie Hausen from the Blue Mountains terrain indicate 1,760 plus or minus 460 kilometers of northerly movement after about 90 million years, which must also apply to rocks of the Bell-Purcell-Windermere block, as they were united as one block at that time. Thus, rocks along the western side of both the northern and southern sectors of the Rocky Mountain Trench exhibit large paleomagnetic translations. 6. Most researchers who have mapped in the area of the southern Rocky Mountain Trench argue that rocks of the Bell-Purcell supergroups are not cut and translated by large displacement strike-slip faults, only normal faults with at most a few kilometers of strike-slip motion on faults in the trench. You can see blocks of Bell-Purcell and Paleozoic rocks lying across the trench here. Thus, no matter whether you find 400 to 430 kilometers or 1,950 plus or minus 600 kilometers of strike-slip motion on the Tintina Northern Rocky Mountain Trench Fault credible, it is enigmatic, because on the basis of matching geology, most researchers have concluded that the fault does not run through the Southern Rocky Mountain Trench, regardless of the continuity of the topographic trench itself, which continues well to the south to Flathead Lake, Montana. Seventh, as the physiographic Rocky Mountain Trench extends continuously for about 1,600 kilometers from Flathead Lake, Montana to the Laird Lowlands, and then continues north-northwestward an additional 1,000 kilometers into Alaska as the Tintina Trench, It is hard to fathom how such a long, linear, and narrow valley could be anything but the locus of a significant strike-slip fault, despite significant evidence for local late normal faulting, especially in the southern sector. Eighth, detailed sedimentological studies documented that the Laramide foredeep broadened slightly during the Campanian, but then migrated northward during the Maastrichtian and Paleocene, the same time as proposed northward migration and the formation of the Laramide thick-skinned thrusts in the Rocky Mountain region. Finally, despite a decades-long intense search by geologists, no other fault, collection of faults, splay, or branch of the Tintina Fault itself has been discovered along which more than 1,000 kilometers of dextral slip might have been transferred. It is difficult to understand how any of the preceding observations can be incorrect, yet no plausible solution has been presented, even though the conundrum has been widely recognized for decades. Next, I propose a testable solution for the problem and then explore some of its tectonic implications. Although I examined the problem about a decade ago, because I believed what everybody told me about the geology, I was unable to locate the fault along which the northerly migration might have taken place. However, a couple of years ago, as I was compiling data for our paper on the collisional foredeep to the 100 million year peninsular ranges orogeny, I was once again drawn to the discontinuities and truncations of several geological features, such as the cutoff of isopachs within the Shaftesbury Formation, part of the foredeep fill to the Peninsular Ranges origin, which is located in northern Alberta and British Columbia, as well as the abrupt southward truncation of the alluvial facies and shoreline of the overlying westerly derived post-collisional molasse of the Dunvegan Formation along the Tintina-Rocky Mountain Trench. You can see the end of the Dunvegan alluvial facies and the shoreline to the southwest on this figure. This caused me to rethink the possibility that the Rocky Mountain Trench was the locus of greater than 1,000 kilometers of strike-slip movement. I found the truncations peculiar, as the Peninsular Ranges orogeny and its hinterland continues southward all the way to Mexico, so it seemed possible that the more westerly portions of the foredeep with their coarse-clastic alluvial fans were simply missing to the south. These truncations, along with the paleomagnetic results for rocks of the Carmack group and the continuous nature of the Rocky Mountain Trench, were compelling and collectively demanded a solution. The outstanding question is, how does a fault with greater than 1,000 kilometers of separation vanish along strike? While there could be many possible solutions, in this case the likely answer turns out to be rather straightforward. A cursory inspection of any tectonic map of the Canadian Cordillera, such as the classic map of Wheeler and McPheeney, coupled with a basic understanding of the ages of thrusting along strike in the Cordilleran fold thrust belt, reveals a geologically plausible solution to the paradox. First, there are two different age thrust belts which approach the Tintina-Rocky Mountain Trench system from the east and broadly occur on opposite sides of the easterly flowing Peace River, or nowadays what is known as the Peace Arm-Williston Lake. Let's look at the Williston Lake area in greater detail. Right here. In the Musqueam Ranges north of the river, the East Vergent fold thrust belt of the Kachika Trough comprises thrust faults, rock units, and facies that widen and continue northward into the Selwyn Basin, where rocks and thrusts were intruded by 99 to 92 million year old post-collisional plutons of the Tombstone Mayo suites. Whereas in the Hart Ranges, which lie to the south of the river, the well-known Cordilleran fold thrust belt of the southern Canadian Rockies, which is temporally complex and has a major pulse of thrusting 54 to 50 million years, as documented by Ben Vanderplume and co-workers. These thrust faults transect and overthrust folds and thrust faults of the older northern belt extending southward from Selwyn Basin. Further north and to the west of the Selwyn Basin, Kachika Trough, thrusting appears to have been related to the 100 million year Peninsular Ranges orogeny, and there the Tintina Fault is readily recognized and mapped as a major strike-slip fault because it is younger than the thrusts to the east. However, south of the Peace River area, where many thrusts are younger than 54 million years, an equivalent strike-slip fault is unrecognized. Instead, the topographic southern Rocky Mountain Trench is generally considered to be dominated by normal or small displacement strike-slip faults, as we saw earlier. These contrasting observations are reconcilable because the northern sector of the strike-slip system postdates 100 million year folding and thrusting in the Selwyn-Kachika region, whereas in the southern Cordillera, many thrusts postdate inferred northward migration as documented by 52 million to 50 million Tectonic paleopoles from the hinterland to the west. Thus, the most likely solution is that the southward continuation of the Tintina Fault within the southern Rocky Mountain Trench was overridden and buried by post-strike-slip thrust sheets derived from the southwest. The trench is now topographically obvious due to Eocene deformation, extensional collapse, and erosion of 7 to 8 kilometers of rock from the thrust stack, which included the Bel-Purcell allochthon, transported northeastward on the Lewis and related thrust faults. The concept of a major tectonic break at the Rocky Mountain Trench is also supported by seismic observations in both the crust and mantle. Seismic reflectors in the lower crust, inferred to represent Cambrian sedimentary rocks just above crystalline basement, were traced continuously westward from beneath the Lewis thrust to terminate below the trench, as you can see here. I suggest you pause this talk and take a look at these. It's fairly difficult to see, but you can see the little seismic lines at the bottom of each section, all the way out to the Rocky Mountain Trench. Similarly, mantle tomography suggests that the thick and cool subcratonic mantle lithosphere of the North American craton was truncated beneath the region of the trench, as shown here. Although outcrops of lower Paleozoic rocks of the main ranges, in light blue and darker blue along the front ranges, are typically correlated with similar age but quite different lithologies and drill core from the subsurface to the east, beneath the interior platform of Alberta, there is no a priori reason that they could not be part of the passive margin deposited elsewhere, perhaps farther south, as they constitute an isolated allochthonous block that restores west of the trench in palispastic reconstructions by Firmer and others. Given that the lower and middle Cambrian cyclic successions, that would be SOC 1 and 2, of the western Laurentian margin, formed in an east-west trending belt close to the equator as documented by Scotese and McCarroll, they likely had similar facies, stratigraphy, and fauna along the length of the margin. Although today they constitute a continuous belt that extends from northwestern Mexico to central Alaska, it is unclear where along the margin any particular fault-bounded sector of the platformal succession formed, especially since carbonate cycles in the main ranges of Canada and in the southern U.S. Great Basin are, according to those who studied them, virtually identical. Thus, on the basis of lithology and stratigraphy, the sedimentary succession in the main ranges was originally part of the North American passive margin, but as it is an isolated block that seems problematic in its current location, nothing rules out it having been transported northward between about 70 and 50 million years. Accordingly, there are no obvious impediments to significant dextral strike-slip movement on the Tintina-Rocky Mountain Trench Fault if the bulk of it occurred after about 70 million years and prior to the early Eocene. Ben Vanderplume and co-workers documented movement ages of a number of faults within the southern Canadian Cordillera using illite age analysis and discovered several discrete pulses that formed temporal belts of thrusting. Middle and late Jurassic, mid-Cretaceous, Cenomanian, and Eocene, from west to east, as you can see here. The ages are reasonable matches for recognized orogenic events elsewhere in the Cordillera, with the two Jurassic pulses matching a widespread 160 million year event and the younger Nevadan orogeny, respectively, whereas the mid-Cretaceous thrusts are a good fit with the 100 million year Peninsula Ranges origin, and the Campanian and Eocene thrusts good matches for early and late Laramide deformation, which are largely coincident with the Maastrichtian to Eocene development of the thick-skinned Rocky Mountain foreland massifs of the Western Cordillera. Although some workers had difficulty accepting the earliest Eocene age for thrusting, a large amount of independent data presented by Kurt Constanius suggests that an early Eocene age best fits movement on the Lewis and related thrusts, and so support the illite ages. For example, in the Wolf Creek area of the Montana Disturbed Belt, a potassium-argon age of biotite collected from a quartz monzonite sill that was folded and cut by thrust faults is 59.6 plus or minus 1.6 million years, whereas an undeformed monzonite dike produced a hornblende potassium-argon age of 47.5 plus or minus 1.3 million years. Both combine to broadly bracket the age of thrusting as earliest Eocene. Although the youngest stratigraphic unit cut by the Lewis thrust is the Campanian Belly River Two Medicine Formation, and the youngest sedimentary unit transected by thrust beneath the Lewis thrust in the foothills belt is the Maastrichtian Early Paleocene Willow Creek Formation, composed of sandstone, shale, and minor limestone, there are no coarse-grained rocks in the formation, despite proximity to the Lewis thrust, which led workers to argue that thrusting was younger than deposition of the Willow Creek Formation. In fact, one of the great enigmas of the Four Deep Basin is the near absence of coarse debris linked to emplacement and erosion of the Bell-Purcell thrust sheets, from which at least 7 to 8 kilometers of rock were exhumed and eroded during mid-Eocene extension. It appears that, except where overlain and protected by more resistant Eocene volcanic rocks, such as in the Bear Paw and Highwood Mountains, any such deposits were eroded. According to Constanius, the oldest sedimentary rocks that might represent debris shed from the allochthons are Eocene sandstone and cobbly to bouldery conglomerate of the 54 to 50 million year Wasatch Formation, preserved beneath volcanic rocks within the Bear Paw Mountains, nearly 200 kilometers east of the frontal thrusts. There, Hearn et al. Reported that clasts within the formation, which decrease in size from west to east, largely consist of quartzite and argillite, derived from strata of the belt supergroup, with lesser amounts of less Cretaceous Paleocene volcanic rocks, possibly derived from the Elkhorn Mountains volcanic field to the west. Farther southwest, but about 100 kilometers east and northeast of the thrust front, conglomerate with clasts of Archean orthogneiss, flathead sandstone, and Paleozoic limestone up to 1 meter across crop out in the Highwood Mountains, where it unconformably overlies incised late Cretaceous four deep fill and is interpreted to represent remnants of an extensive early Eocene alluvial fan complex, which in turn was overlain by 52 plus or minus 1 million year potassic volcanic rocks. Constanius used those data to suggest that the Wasatch Formation and related conglomeratic units represent the youngest units related to shortening in the fold thrust belt, whereas the overlying early to middle Eocene potassic rocks represent magma erupted and intruded during widespread extension. Thus, the early Eocene illite ages reasonably reflect the emplacement of the Bell-Purcell allochthons, as well as thrusts structurally below them in the foothills belt, which collectively serve to indicate that thrusts postdate the majority, if not all, of the northward migration indicated by paleomagnetic studies of the Carmax volcanics. Not only is the age of thrusting important, but it is also critical to quantify the amount and direction of shortening in the fold thrust belt to evaluate whether or not the Bell-Purcell allochthons and others might have been transported from west of the Rocky Mountain Trench and so qualify as candidates for rocks that traveled northward in the same block as rocks of the Carmack groups and in the Blue Mountains. The McConnell thrust forms the boundary between the Front Ranges and foothills geological and physiographic provinces. The fault system, which has a spectacular set of frontal duplexes similar to those recognized in frontal thrust zones elsewhere, such as the Moyne Thrust of Scotland and the Blue Ridge of the Southern Appalachians, was linked to the Livingstone thrust further south by Fermer, who, along with McMecken, estimated a minimum of 40 kilometers of eastward displacement on the system, but total transport of the thrust sheet was at least 100 kilometers when the shortening on thrusts and folds of the structurally lower foothills belt is included. But really, there's no similar rocks to those found west of the McConnell thrust, west of the McConnell Livingstone thrust in the footwall. Firmer also found a minimum of 90 kilometers of shortening on the Lewis thrust system, and those transport distances are summarily shown on the figure as long arrows, using the 235-degree transport direction he suggested. With these parameters, the front ranges restore approximately to or just west of the Rocky Mountain Trench, and the Belt-Purcell block, the main ranges, and the Windermere allochthons, in part transported on the Lewis and other thrusts, all restore west of the trench as shown. It must be emphasized that because the rocks in the thrust sheets do not have corresponding cutoff units in their footwall, estimates of transport distance are minima. Next, we look at this area in some detail. The approximately 100 million year Crow's Nest volcanics, which are alkaline slab breakoff volcanics, erupted during the Peninsula Ranges orogeny, transported eastward on the Livingstone thrust, and unknown in sections farther east, yielded a shallowly inclined paleopole discordant to the Tectonic pole by Ted Irving and others. Those authors indicated that if the sample span is sufficient time to average out paleosecular variations, then the paleopole suggests a paleolatitude 1900 plus or minus 700 kilometers farther south, which is of similar magnitude to other Cretaceous rocks from the Cordillera located farther west. Although the authors considered the idea that the rocks were transported northward, then thrust onto the North American craton, they stated that there was insufficient evidence to demonstrate that the paleosecular variation was averaged out, so could not reasonably conclude that the rocks had been transported northward, although they could not rule it out either. Because the paleopoles from the Crow's Nest volcanics match the paleopoles of more westerly units, I conclude that although additional paleomagnetic study of the Crow's Nest volcanics is certainly warranted, the available data are nevertheless consistent with the idea that rocks of the front, main, and western ranges, which all lie structurally above and west of the McConnell-Livingstone thrust, were transported northward, then placed northeastward over the Rocky Mountain Trench. At a higher structural level than the McConnell-Livingstone thrust system, the total amount of displacement on the Lewis and related thrust faults, which carry the rocks of the Belt-Purcell supergroups, is unknown, as again, there are no Mesoproterozoic rocks in the footwall comparable to those in the hanging wall. However, if we look at the Helena salient shown here, a minimum overthrust distance might be gleaned from the cool water culmination, which is an oval tectonic window where rocks beneath the basal thrust of the Belt-Purcell allochthon are exposed. Detailed studies by Karen Lund and others, who named the fault there the Lowell Thrust, showed that metasedimentary rocks beneath it were deposited after 98 million years and prior to intrusion of an orthogneiss dated at 86 million years. Given that the rocks of the Belt-Purcell allochthon block are continuous for over 400 kilometers to the east, where they also sit structurally upon Cretaceous rocks, and they are known to be thrust over Cretaceous sedimentary rocks in the Kimpton Ranch drill core, under the Devil's Fence anticline, just east of the boulder batholiths, it seems that the entire allochthon, including local slivers of crystalline basement, was derived from west of the cool water culmination and transported a minimum of 400 kilometers to the northeast after 86 million years, similar in magnitude to overthrust distances of other megathrust sheets, such as the Blue Ridge Piedmont sheet in the southern Appalachians. Thus, data from stratigraphy and paleomagnetism, as well as age, direction, and minimum distance of thrusting, all allow and suggest that rocks of the Belt-Purcell supergroups and their Neoproterozoic and Phanerozoic cover were transported northward during the Maastrichtian to Paleocene and then placed northeastwardly as massive allochthons on the Lewis-McConnell-Livingstone thrust systems over the strike-slip faults of the southern Rocky Mountain Trench and Cretaceous rocks of the western interior basin during the early Eocene. This is an important conclusion because Mahoney et al. Recently made a case for deriving detrital zircons in the Nanaimo Basin of the insular terrain on Vancouver Island from rocks of the Belt supergroup, which they then used as evidence for a minimum displacement model for western Baja BC terrains, as today the two areas differ little in latitude. However, their model is untenable if the rocks of the belt supergroup were transported northward along with the more westerly terrains, which is indicated by the paleomagnetic and geological data. Here is an age versus apparent latitudinal migration plot for sedimentary rocks of the coastal and Baja California to illustrate the similarity in age and migration distance with rocks in southern Canada. Note that just as with the southern BC dataset, the farthest traveled rocks were deposited at about 70 million years, and by 50 million years, the rocks generally have cratonic paleopoles. The northerly displacement of about 1,300 kilometers proposed here by restoring matching geological features is within error of nearly all pre-55 million year paleomagnetic samples, similar to the northern dataset. Overall, and as pointed out by Merle Beck over 30 years ago, the data for bedded rocks from the entire Cordillera over the age span of 70 to 50 million years are remarkably consistent from north to south and support the far-traveled results. Here is a summary diagram showing many of those paleomag results and where they might get restored to based on the paleomagnetism. I propose that two of the three geological regions of the Cordillera recognized by Phil King in 1969 on the basis of geological differences across two transverse zones, the Lewis and Clark transverse zone, which extends from Vancouver Island to the thrust belt in the Helena salient, and the Texas lineament, which can be traced from the transverse ranges of California through the Mojave and Sonoran deserts to the Gulf of Mexico, could be palinspastically restored to a continuous zone that constrains northward translation of the Cordillera to about 1,300 kilometers. In addition to the two transverse zones, such a reconstruction restored several other features as follows. Two widely separated sectors or belts of Upper Cretaceous, early Cenozoic, post-collisional plutons with distinctive and comparable slab failure signatures as documented by Hildebrand and Whalen are reunited in this reconstruction. The two belts approach the proposed fault at a high angle. Porphyry copper deposits, shown here in blue, of the Butte Porphyry Copper District of Montana, align with porphyry copper deposits of the U.S. and Mexican Sonoran Desert. Two segments of the deformed and metamorphosed Laramide hinterland belt that was exhumed and collapsed during and after emplacement of the plutons are combined into a continuous belt. In restorations of Southern California, the eastern occurrences of the Pelona and Orocopia subduction channel schists form an east-west band extending across much of the Southern California and western Arizona. They constitute a close match with the high-grade Swakane gneiss located in the high Cascades of Washington, as I originally suggested over a decade ago. Two segments of a likely continuous belt of Eocene magmatism and extension are reunited in the proposed reconstruction. The Mexican and U.S. regions of Miocene basin and range faulting, which exist immediately south of their respective transverse zones, are restored to a continuous region of extensional faults. This restoration suggests that the crust in both regions was similar and continuous prior to northerly translation. The Omineca belt, which, as we saw earlier, is a hinterland-like component with 125 to 105 million year thrust metamorphism plutonism, seemingly orphaned without an associated fold thrust belt in Canada, matches well with the thrust faults and foredeep of the Wyoming-Utah severe orogeny east of the Cordilleran hinge line. Here is a possible reconstruction of the southwestern part of North America prior to 70 million years and the northward migration. Note the continuity of the 80 to 58 million year Laramide collisional belt with its post-collisional distinctive slab failure plutons and the correlation of the Swakane and Orocopia schists. In my next talk, Part 2, I'll look at the implications of the northerly migration and its timing on other features in the Cordillera. For those of you who found the talk rather technical, I offer this simpler explanation.